Hopefully you're a little familiar with vectors from either your geometry classes or your science classes deal a lot with vectors. We're not going to do anything as complicated as your science classes with them, but what we are going to do is learn how to describe them, learn how to draw them, learn how to do operations to them, that kind of stuff. So one thing you may already know from your science classes is that a vector is a quantity specified by a magnitude and a direction. It's got to have both of those things included. If it's just a quantity that's specified by a magnitude, then it's not a vector. It's what we call a scalar. Okay, so if I gave you an example that I was driving 65 miles per hour due north, so straight north, that's a vector because I'm telling you the size of my speed, the magnitude of my speed, and I'm telling you the direction I'm heading in. But if all I told you was that I was driving 65 miles per hour, then I've just given you a scalar. My speed is a scalar. My velocity is a vector, so you might want to note that this is a velocity and this was just my speed. Okay, so what we're going to do is we're going to alternate through this packet. I'm going to do one question for you, then you're going to do one on your own, and that's how we're going to work. I think that ends up meaning you have to do 4 questions or something like that, so it shouldn't be too bad. Okay, so when we describe a vector, you give a direction and a magnitude, and we're going to be using a lot of methods. We're going to go back very, very briefly, just on a couple questions, to some very easy course and bearing kind of measurement. But we're not going to do that a lot because we have other ways of describing our vectors that we're going to use more. But for example, this question 1 right here, this vector says that it represents a distance of 5 meters, and it represents that distance at an angle of 30 degrees east of south. So you have a variety of ways of describing that. You could say 5 meters at 30 degrees east of south. Okay, remember that when you do that, when you measure in that format, that is bearing. That is something that we have done before. So you could have also said on a bearing of south 30 degrees east. So that would have been another way to measure it. You could have even calculated that if this was 30 degrees, then this angle over here would have been 60. So you could have used that angle to indicate the direction. So there's going to be a lot of different angles or ways of stating the direction that that vector is headed in. So once you've watched this video, then you can either go back and do number 2, or you can pause really quick and go ahead and write number 2 down, write your answer down, and then we'll check that in class. Okay, so that's how you describe vectors. I know it's very brief because it should be very easy. Okay, so then the next thing would be to add the vectors, and there's going to be a drawing way or a graphical way of doing it, and there's going to be an algebraic way, which we'll get to later. So when you draw a vector, it's got 2 parts to it. It's got the tip, which indicates the direction that the vector is headed in, and it's got the tail, which indicates where that vector started or where the origin was. So vectors are commonly denoted as an arrow where the tip indicates the direction of the vector, and the tail depicts where it started or where the origin was. And the longer you draw a vector, the greater its magnitude. So if you compare these 2 vectors right here, vector u is longer than vector v. So vector u would represent that it's got a greater magnitude than vector v. Okay, so you just need to keep that in mind as you're drawing these things. So what we're going to do is we're going to add these vectors, and of course subtracting. That's the same thing. But we've been given 4 vectors, u, v, s, and t, and we're going to add u plus s. So what we're going to do is we're going to start out, we're going to draw, essentially what we call like our point of origin, so I'm going to call it O, right? and vector u would displace me up and to the right. And what I want to do is, this is all estimating, it's all kind of eyeballing. You know, back in geometry, you guys actually would have taken the patty paper and traced it and actually drew them the correct length and the correct direction and everything. We're not going to be that detailed. So I'm going to draw a vector that looks like it's headed the same direction as you and about the same length as you, right there. So if I started here at my origin and I traveled along vector u, and then it says to add vector s. So what that means is that I traveled along vector u, and now I also want to travel along vector s. Well, I'm not going to start back here at the origin because I'm no longer there. I have now traveled along vector u. I'm now standing right here at the end of vector u. So what I do is vector s would take me straight to the right. It looks like it's almost as long as vector u. They're almost the same length. So I'm now here. I'm going to go ahead and change colors so you can see where I am. So I'm now here, and now I'm going to travel about the same distance but straight out to the right. And so I traveled along vector s. Okay, so what we've just done is we've added those two vectors, what we call tail to tip, because you figure out the tail of the first vector is essentially your starting point, your origin. You travel along the first vector, you now get to a new location. And so when you're ready to travel along the second vector, you don't go back to the beginning. You start from where you are now. Okay, and what has happened is, let's change colors again so you can see this. What has happened is this is where I started, and this is now where I have ended up. Okay, this is what we call the resultant vector. And I mean, you can give it a new name, but usually we would literally just call it vector u plus s. Okay, and so that's this blank right here. The vector created by these kinds of operations is the resultant. It is the result of traveling along some vectors or multiples of vectors, or traveling in the opposite direction of vectors. It's the result of all these operations. Now the other thing is that you need to be aware that these operations are commutative, meaning that I could have done u plus s, which is what I did, but I'm going to get the same answer as if I did s plus u. Okay, so I need to erase this little vocab right here so you can see what's going to happen. Okay, so let's say that I wanted to prove that. So I go back to my point of origin, and I want to prove that if I did s first and then u, I would end up in the same place. I'd get the same resultant. So if I start here at my origin and I go straight out to the right, however long I think s looked, and I'm now here, and then I travel along vector u, which would start out here and it would take me that up and to the right. Sure enough, I end up at the same place. So this resultant vector would be the same. From my starting point to my ending point would be the same. Okay, so that's what makes these commutative. Okay, so what we're going to do is I'm going to do question 4 for you, and then you're going to do question 5. So, because I want to do a different kind of operation as well. What we're also going to do is we're going to do what's called scalar multiplication. So remember, a scalar represents just a quantity. That's it. It's just got a magnitude, so it's a constant. Okay, and so we're going to take our vector, we're going to multiply it by a constant, and the result is that it's going to either stretch it and make it longer, it's going to compress it and make it shorter, or if you make it negative, that simply means that instead of going, 60 miles north, you're going to go 60 miles south. So it simply moves it in the opposite direction. So what I need to do is I need to just really quick, I need to sketch what it is that s and v look like, because those are the two that question 4 will be operating on. So s was the vector that went straight out to the right about that far. Okay, and then v was a vector that went down and to the left, and it was quite a bit shorter. So v looks like it does this. That looks like a good representation for v. And so what question 4 asks me to do is it asks me, I'm going to draw. Here, I'm going to call that my starting point right there. Just random point in space. And what it says I'm going to do is I'm going to travel along S. Okay, so I draw vector S, make it about the right length, headed directly to the right, so it's in the right direction. And then what I'm going to do is I'm going to travel vector V twice. I'm going to make it twice as long. So let's say that vector V just represented 1 foot. I'm actually going to travel 2 feet. But the minus right here means that instead of going down and to the left, I'm going to go up and to the right. So vector V would look like this if I went in the opposite direction, and I'm going to travel 2 of them. So here's a V and here's a V, and it's the opposite of it because I'm going up and to the right. And so the resultant vector, or the result of traveling that path where I did S and then I did the opposite of V twice, has moved me from here to here. And so this is what we would consider the resultant vector. Okay, so you guys will try 5, and that will be one that we will check in class tomorrow. Okay. Now, fortunately for all of us, including Miss P and I, we are not going to draw a ton of vectors. I mean, it's a TEK, we have to do it, but you guys know that we prefer algebra whenever possible. So what we're going to do the majority of the time with our vectors is we're going to resolve our vectors into their components. And it's just another way of measuring a vector. So what it means is that instead of, on this example right here, instead of saying that this vector, let's go ahead and name it, let's call it vector A, okay? So instead of saying that vector A is 11 meters, and I'm going to go ahead and use bearing. I mean, you can use whatever description you want to, but instead of saying it's 11 meters on a bearing of, north 49 degrees west, okay? What I want to do instead is I want to break it up into components. And when we do that, we put those components, it's going to look like coordinates, it's going to look like an ordered pair, but we put them inside arrow brackets, and that means that it's not just an ordered pair, because all an ordered pair is would be a point in space. By putting it in the arrow brackets, what we are doing is we are saying that instead of just ending up at a point, that we actually traveled that distance horizontally and vertically. And the way that we do it is with that same process that we used last semester. Don't worry, this is about as extensive as the trig gets this year. Okay, we're going to make a right triangle out of it. And so here's the origin. Here's where my vector put me. It's where I ended up, right? And so I ended up at the point xy, right? And the x-coordinate will tell me how far to the left of the origin I am, and the y-coordinate will tell me how far above the origin I am. So your x and y components make a right triangle out of your vector. Okay? So what that means is that we can use just basic SOHCAHTOA right triangle trig to evaluate and break this up into our components. Okay? So what I'm going to do is I'm going to do that. I'm going to create some space here to do the actual work. Okay? And so what I have is, if this angle right here is 49, then this angle right here inside the triangle is 41 degrees, because of course they have to add up to 90. So the sine of that 41 degree angle would be the opposite side, which would be this side over here. That's the one that's opposite from my angle. So y over the hypotenuse, which is the vector. It's the length of the vector, which is 11. So that means to find the y component of my vector, or to find the y coordinate where I'm standing, I would just do 11 times the sine of 41 degrees. Okay, and then to get the x-coordinate, because I need this side right here, now I'm looking for the side that's adjacent to the angle inside the triangle, so I would do cosine of 41 degrees is equal to the adjacent side, which is that x-coordinate I'm looking for, over the hypotenuse, which is once again still just the length of the vector, which is 11. So to find the x component of my vector, okay, I would simply rearrange that and I would multiply, and I would do 11 times the cosine of 41 degrees. Okay? Okay, so this is what I get when I type that into my calculator. I get that my y component is 7.217 and my x component is 8.302. Okay, now there's two ways that I can write that. So I called that, what, vector A? So vector A, okay, what I want to do is I want to keep in mind a couple things. First of all, I need to make sure I put them in order, first x and then y. I'm going to always do horizontal before vertical. The other thing is that this x value right here is a positive number, but it's headed to the left. So I'm going to need to make sure to attach a negative to it. So when I'm writing the components, what I do is I put the arrow brackets and I write negative 8.302 and positive 7.217, and I close the arrow bracket. And so what that tells someone who's reading it is that vector A has displaced me, it has moved me 8.302 units to the left from where I started and 7.217 units above where I started. You don't want to write it like this because it puts you in the correct location, but it doesn't tell you which way you actually went to get there. For all we know, we could have gone, up and then left and then down and then right, and we could have done some zigzagging, and this would have been where we ended up. But we don't know that it's actually the direction we moved and how far we moved. So you don't write it as an ordered pair. You write it as arrow brackets, or one way you'll see Forrester do it when we do some practice problems in groups soon is he'll attach what's called a unit vector. And we're going to do some warm-ups and some more practice. We're definitely going to practice unit vectors. But instead of putting the arrow brackets and the commas, what he does is he writes it as kind of an equation, and each component is attached to what we call a directional unit vector. I represents a vector that would displace you 1 unit horizontally. So it's the horizontal unit vector, and this is saying you're going to travel horizontally times 8.302 and then in the negative direction. And then J is what's called the vertical unit vector, and it's a vector that would displace you just 1 unit straight up. And so multiplying it by 7.217 says you're going to travel 7.217 units straight up. So this and this, they're interchangeable. You'll get a choice as to which one you use, but you need to be able to read them because we will use them interchangeably. Okay? And then the final couple of topics, because I know we're running a little long. If you know the components of a vector, then you can find the magnitude and the direction. So it's essentially going back and forth between the two forms. So this vector started me out here and it moved me to here. So let's just call this vector V, okay? And so vector V, we know its components. We know that it has displaced us 11 units right and 14 units up. Or we could write that as 11I plus 14J. Same thing, okay? So we know the component form. If we want to write it in the original form that we started at the beginning of the notes, then we need to know how long this vector is. So we need to know the hypotenuse. And we need to know this angle right here. So to find the magnitude of the vector, to find the size of the actual vector that you traveled along vector v, you're looking for the hypotenuse of a right triangle. So the way that we would say that is we would say we want you to find the magnitude of vector v, and it's going to be written one of two ways. It's going to be written inside of single bars or double bars. So it looks kind of like you're taking the absolute value of it, or if you understand greatest integer, it kind of looks like that. But all we're using is the Pythagorean theorem to find it. So this right here, the Pythagorean theorem says that the x component squared plus the y component squared is equal to the length of the vector squared. And so all we do is we get rid of that squared by square rooting both sides. So if I want to know the magnitude of vector v, then I'm going to do the square root of my x component squared, 11 squared, plus my y component squared, which is 14 squared. And when I do that, I get a magnitude of 17.804 meters, because the other components were in meters. And then I need to know this angle right here, because that'll tell me the direction that I'm moving in. And so I know the side opposite from that angle and the side adjacent to that angle. So I do the tangent of that angle is the opposite side, which is 14, over the adjacent side, which is 11. And so that means to find that angle, I'm going to do inverse tangent of 14 over 11. So I know that it is some trig again, but remember it's all right triangle trig, so nothing too complicated. And so the angle that we get is 51.84 degrees. Okay, so vector v could now be written in its alternate form. Instead of writing it in its component form, okay, we could also say that vector v is 17.804 meters at 51.84 degrees north of east, because this direction is east and our angle went north of there. Okay, so alternate ways of writing the same thing. And then the final thing is to perform vector operations. So instead of adding them and having to draw the pictures, you can do them much more quickly by simply adding or subtracting their components. And you can do the same thing with scalar multiplication. Instead of having to physically draw a vector twice as long as normal or 3 times as normal, then what you can do instead is you can multiply both of the components by that scalar, which makes it a lot less work because there's very little drawing. Okay, so what this final problem that I'm going to do for you guys here says, what is v plus w? So vector v moves you 3 units to the right, and then vector w moves you 2 more units to the right. So v plus w would go 3 units to the right plus another 2 units to the right. And then vector v moves you 4 units down, and then vector w moves you another 8 units down, so I'm adding another 8 units down. And so what that means is that vector v plus w has displaced me 5 total units to the right and 12 total units down. Okay, so that's v plus w. Then here I'm asking you for the magnitude of that resultant vector. Okay, so you don't need to draw a picture, but I want to show you what it is we're talking about. We're talking about a resultant vector that has displaced us 5 units right and 12 total units down. So we started out here and we ended up displaced this far away. So once again, we're doing the Pythagorean theorem, And we're doing that Pythagorean theorem with these two components. This is our x distance and this is our y distance. And so when I want the magnitude of v plus w, okay, I simply plug these two new components into the Pythagorean theorem. So square root of 5 squared plus negative 12 squared. And so I get a magnitude of 13. So I am now 13 total units from where I started. That has been my displacement. Okay? Okay, so then the final thing for this problem, and I'm going to have to erase because my handwriting is huge, is I wanted to practice finding this magnitude instead, and I want to find the direction. So I need to know this angle right here to get the direction of my resultant vector, and I want to find the magnitude of each of these separately. So the magnitude of vector v, if you want to pause for just a second, do the Pythagorean theorem with 3 and negative 4, and what you'll get is a magnitude of 5. And then when you do the magnitude of vector w, and you do the 2 and the negative 8 as your components or your legs for your right triangle, what you end up with is the square root of 68. And so I'm going to need to erase, make some room here. Okay, the magnitude of v plus the magnitude of w is going to be 5 plus the square root of 68. It doesn't simplify. I mean, 68, the square root of 68 would simplify, but it still wouldn't make the numbers combine. So you can leave it like that. And then the direction, I'm going to do the same thing I did in the previous problem. Tangent of that direction angle would be the opposite side, which is the vertical leg, so negative 12 over the adjacent leg. So I'm going to do inverse tangent of negative 12 over 5. And when I do inverse tangent of negative 12 over 5, I get negative 67.38 degrees. So I could say that my resultant vector is a vector that is 13 units in size at that directional angle. Okay, so now you guys try 8 and we'll check it in class. So I'm sorry these ran so long. It's a review of several years of possible vector information. So we're going to move from here, practice from here, and continue adding new stuff every day. Thanks.